We will now develop an approximation algorithm for multi-weight cut using the definition of the isolating cuts. Remember, the isolating cuts we can find efficiently. Can you come up with a simple algorithm that uses our algorithm for isolating cuts that finds a valid multi-way cut? I'm sure that you found it. You just take an isolating cut for every terminal that separates it from everything else, and if we do that for every terminal, then in the end they will all be separated. But if you're very smart, then maybe you also found a small improvement. So what we can do is first, for all the terminals we have, we compute a minimum cost isolating cut. And then we take only the k-1 cheapest such isolating cuts. So basically we ignore the most expensive one. Why can we do that? Let's say that the isolating cut for ck is the most expensive one. Then we pick the isolating cut for c1, removes t1 from everything. Then we remove t2 from everything, and so on. And in the very end, we remove tk-1 from everything. We don't need the cut for tk anymore, because already everything else is separated from tk. So one of those we don't have to take. Only k-1 ones. So what is the cost of this union of k-1 isolating cuts with respect to the sum of all these isolating cuts? Well, we pick k-1 cheapest ones, and there are k in total, so we can use the pigeonhole principle to show that it's at most k-1 over k. And the pigeonhole principle tells us the most expensive one costs at least as much as the average. So the most expensive cut, let's say C1, costs at least as much as 1 over k times the sum of all cuts. It costs at least as much as the average. So if we remove it, then we remove 1 over k from the sum, so we get k-1 over k times the sum of those isolating cuts. So with this information, what do you think is the approximation factor of this algorithm for multi-way cut? We will show that the approximation factor is 2 minus 2 over k. To do this, again, we assume that we know the optimum. We know the optimum multi-way cut A. For example, if we have these terminals here, this might be the optimum multi-way cut. And now we take this multi-way cut, and for every terminal Ti, we take out the edges that connect the component of Ti to something else. So for example, here we have these 4 edges that connect the component of Ti, the component Ki, to another component. So our set Ai is exactly these 5 edges. It's all the edges in A, such that one vertex lies in Ki and the other one does not lie in Ki. We do the same for all the other terminals, so we get also the set Aj here. And what special properties do these sets Ai have? Each of them is an isolating cut. The set Ai is an isolating cut of Ti, because all the other edges that are not in Ai, they don't influence what this component is connected to at all. These are exactly the edges from the multi-way cut that remove Ti from anything else. And what other observation can we find? Can we somehow estimate the cost of A in terms of these AIs? Well, first of all, every edge of A must lie in one of these sets. If it doesn't, then it doesn't have to be in our multi-way cut. We could just get rid of it. It doesn't connect any of these components anyways, so why should it be in the multi-way cut? And what about the cost of A? For that, just pick any edge of the multi-way cut. For example, this one. This connects 2 components. Here, the component Ki and the component Kj. That means that this edge belongs to the set Ai and to the set Aj. So it belongs to exactly 2 of these sets. And that holds true for all the edges in multi-way cut. Each of them belongs to exactly 2 of these sets. So the sum of the cost of these Ai sets is exactly twice the cost of A. Can you finish the proof from here? The optimum for our problem is exactly the cost of A. And the cost of A is exactly 1/2 the sum of all these sets. And all these sets gives us isolating cuts. So AI is an isolating cut of Ti. Now if we calculate the minimum isolating cut of Ti instead, then this can only get cheaper. So the sum of all these AIs is at most the sum of all the optimum minimum isolating cuts Ci. And then from these isolating cuts, we take the k-1 cheapest ones. And that we showed on the previous page, that gives us k over k-1, the cost of what we have in the end. And this finishes the proof. Again, the final question. Is this analysis sharp? Is there an instance where our algorithm really achieves only this approximation factor and not something better? Try to construct one. For that, we again start with some complete graph on k vertices. So for example here, I pick only 4 terminals that we can still see something. And then on every edge I place another vertex. So these are not terminal vertices. So basically I replace every edge with a path of length 2. And the cost of all the edges we set as 1. Now what is the isolating cut of this vertex? Now what is the cheapest isolating cut of this vertex? It's connected to 3 other ones. We have to remove at least 3. They all cost the same, so let's just pick these 3. What's the minimum cost isolating cut for this one? Well, from now on everything is symmetric, it's a complete graph. So all the vertices behave exactly the same way. It means that this is a minimum isolating cut for this terminal, this is a minimum isolating cut for this terminal, and the remaining 3 edges would be a minimum isolating cut for the remaining terminal. But we don't pick the last one, we only pick k-1, so our solution picks all except k-1 edges. So we have k-1 times k-1 edges. What about the optimum? We can start again with this vertex. We pick a minimum cost isolating cut. But then if we continue with this vertex, we don't have to pick this edge, because these 2 are already separated. It's overkill to pick this edge as well. So we could just pick these 2. And then for the next one, we don't have to pick these 2, we only have to pick the last one. So every step we can pick 1 fewer edge. So it is enough to pick the sum of 1 to k-1 over I. So basically for the first one k-1, then k-2, then k-3, and so on up to I. And this formula is k times k-1 over 2. And now if we want to... And now what is the exact factor we get from these? So we have to divide alg by opt. These 2 here cancel out, and then we get exactly 2 times k-1 over k. And this is the same as 2 minus 2 over k. So for these instances, we really achieve exactly our approximation factor. Are there better algorithms? Again, the answer is yes. There's an algorithm by Sharma and Vondrak from 2014 where they achieved the approximation factor 1.2965 minus 1 over k. So this is already substantially lower than a 2. On the other hand, and this is very interesting, just 2 years ago people could show that we cannot approximate this problem with the factor 1.20016 minus order of 1 over k, unless p equals np. So here for this problem, the upper bound and the lower bound are quite close together compared to what we've seen before. But still there's a gap, and the last algorithm that gives us an improvement has already been 6 years ago. So maybe there can be some progress made here, and one of these 2 bounds can be improved. That's it for the 3rd lecture. And next week we will have an excursus on linear programming that gives us a whole new world of approximation algorithms. Thank you for watching.